So today we will discuss about further. We will discuss the band structure calculation. In the previous lecture, we discussed about how to calculate this band structure. Uh, so, mm, the Brilliant zone path for band structure calculation. The important thing is basically the band structure or the Brilliant zone path. So the Brilliant zone path you need to determine. So I showed you some examples that here for the cubic lattice you can see that what is the Brilliant zone path for the cubic structure, simple cubic, and for the BCC body center cubic, here is the uh, Brilliant zone path. The same is for the FCC, you can find the path here, and the third one is the tetragonal lattice. So the Brilliant zone path for the tetragonal lattice structure, and so on. There are here is one paper, high throughput. I will just show you the title of that paper if I can find. Let me check where to find that paper. Here, in this paper, high throughput electronic band structure. Here, in this paper, you can find this is the title of the Computational Material Science Journal, and here you can see the high throughput electronic band structure. You can see that almost every structure detail is here. You can see FCC. Here is the cubic lattice and BCC and TET and BCT1, BCT2, orthorhombic, base center orthorhombic. Here you can see this paper. In this paper you can find the Brilliant zone path for each possible structure in the crystal lattices. So anyhow, let's back to the topic. So here you can see. So this is the ordinary, like the general band lines format, which you can write this way in the CSTA input file. And for example, if your structure has some transition metals or other metals, then how you can uh, calculate the band structure. So usually the uh, DFT basically underestimate the band gap. So then you need to, especially for the transition metals. So for the transition metals here, you can see that the for titanium in this case. So we consider, so this is the black LDA U projected. So this tool tells us about the number of shells of projectors. So here we consider this n is equal to n and l. So one is the principal quantum number and the other one is the angular momentum quantum number. And in the so for 4s, uh, 4s2 the last, and 3p6. So n is equal to 4. So this 4 represents this 4s2, and for s the angular momentum quantum number is 0, and for n is equal to 3, that is 3p6. So this is 2, and the angular momentum quantum number is uh, uh, 2. So for S it is 0, for P it is 2, and D and F it is like that way. So you need to put this. This is basically we call it the in order to consider the transition metal orbitals so that we can find the correct band gap of the required structure. And next one is the optical properties. So for the optical properties, let's calculate imaginary part of dielectric function and store it. So when you make the optical calculation true, so in Siesta output file, it will create the system label means that the name in the input file for the label you give that name, and so that name dot EPSI mg. This file it will create, which tells us about the that this file has the information regarding the optical property. So for optical energy minimum, you need to give the value, and for maximum, actually it is the range. And optical broadening means that it broaden the Gaussian broadening to the frequency value. And optical seizure we apply. So DFT calculation underestimate the band gap. So seizure operator a rigid shift of the unoccupied state. And it is only applied to the optical calculation to correct the gap and improve the results. Okay? Optical number of bands. So we want to calculate all bands. So this control basically the number of bands that are included in the optical property calculation. And this is the optical block optical dot mesh, the mesh size used for the integration across the bridge and zone. For example, in this case we wrote like this: block optical dot mesh of 5 along x, 5 along y, 5 along z, and block. So the three values represent the number of mesh points in the direction of each reciprocal lattice. Optical mesh offset if it is false. So if set to true, then the mesh is offset away from the gamma point for odd number of points. And optical polarization uh, type, so polycrystal. So for polycrystal, you can calculate polarize, which implies the application of an electric field in a given direction, and unpolarized means that it implies the propagation of light in a given direction. So one is the electric field in a given direction for polarized, for unpolarized light propagation in a given direction. And polycrystal, in the case of the first two options, the direction in space must be specified for the electric field or propagation using this. So vector block is this. So you can mention this optical polarization in this way, which is the block optical dot vector. So you need to mention this way. So if you can see here that 1.0, 0.0, and 0.5. This means that this field is basically applied in the x and z direction. Okay. So this is all about, and we can calculate other properties also from this. Uh, um, like for optical properties, copy this EPSIMG file to the SASTA utility, where you can, if it is the first time, then you first need to make run the command make, and after that G Fortran input dash O input, and then G Fortran optical this. So you need, there are two files. These two files you need to compile, and finally we will use so dot input and our the output which is given by the siesta during the optimization. So this is the system level material name dot EPSIMG, and when you run it, so it will give you the output file which is e2.date.spin1 to e2 this one. So then we will convert this to e2.date, and that e2.date we will use with the optical. So in the optical there you need to run two times. Okay, first you need to run with the input dot slash input the EPSIMG file, which gives you the e2.date.spin1, and then you rename this e2.date.spin1 to e2.date. And then this e2.date we will use with the dot slash optical, and this one, which will generate the optical files. And that optical files will give us e2.dat.spin2, which we will also convert to e2.dat and use the above command. This will generate optical files like refractive index, reflectance, conductivity, uh, what else? Optical conductivity, optical absorption, and other files it will generate. Okay, so this is all about this thing. So the important thing is that, as I showed you, the optical properties here, like optical minimum energy. So here in the input file, you can see that optical calculation. So optical calculation here is true, and here we wrote capital T. So you can either use complete true word or only T you can write. And optical number of bands. So we mentioned 300 bands. And optical energy minimum here is the 0 RY. So we convert this RY to electron volt. So 0 electron volt is the minimum energy for optical energy calculation, for optical calculation, and optical energy maximum is 20 electron volt. Okay, and optical broadening we apply this 1 electron volt, and here optical scissor we apply 0. And this is the optical polarization type. So let's move to the second slide. So here you can see the total number of bands here mentioned. So here 300. And optical polarization type we wrote polycrystal, and here you can see 1.0, 0.0, 0.5. And optical mesh is 1, 20, 20. So this is the optical mesh we applied. And what else? So this is all about this thing. And here you can see that we mentioned like this block. So let me make it colorful so that you can understand it. And make it bold. Yes. Here you can see. So the optical, this is the Ti is equal to 2, this is the number of shells of projectors, and n is equal to 4. So 4 represent n and 0 represent L. And here n is equal to 3 because we are calculating two orbitals. So n is equal to 3 is the principal quantum number, and 2 is the angular momentum quantum number. So this way when you mention in the input file, so it will calculate all the properties. The same is the case for the, if you want to calculate the projected density of states, P DAS, which we call it. So you need to mention here everything in siesta we need to mention in a block. So projected density of states, so minus 25.0, 10.0, 0.25, and 500 electron volt. This is the projected density of states plan. So projected density of states we will discuss in other lecture, but this what I want to show you here is the projected density of states. Okay, so for density of states, we the CST will create when you mention this block in the input file during the optimization, so it will create the PDAS file dot system level dot PDAS file, and that PDAS file we will take it to the CST utility, that is PDAS XML directory, and if it is for the first time, of course, then you need to make the make command, and PDA, when you make it, so it will create PDAS XML executable file, and this dot slash PDAS XML, and this just generated PDAS file, you will run with that. So it will, when you enter, where is this? Eh, when you enter that, so it will give you the output. So press enter,